Okay, so very good morning to all of you. So we are talking about DES. So today we'll talk about the cryptanalysis on DES or attack on DES. So in the last class we have described the DES, full round DES. So DES is a block cipher. It's a block cipher, and block cipher is a symmetric key encryption. So it is a 64-bit 16 round block cipher. 64-bit block cipher, and the round 16 rounds. So you have 16 rounds, and the key size is 56 bit. So it's basically text to input. One is the plain text, which is 64 bit. Another one is the key, which is 56 bit, and it gives us a ciphertext, which is also 64 bit. So this is plain text. This is ciphertext. So this is the encryption. This is what Alice is doing. Alice is encrypting a message M. Alice is encrypting a message M using the key and generating the ciphertext. And inside this we have many rounds. For this guy we have 16 rounds, and for each round we need to have a round function, and then we have finally at the end of the last round, the output of the last round is nothing but our ciphertext. And that ciphertext Alice is sending to Bob over this public channel. So now Bob is having the same algorithm. Everybody is having the same algorithm. Algorithm is public, and Bob is having the same key. So Bob can do the reverse of this encryption. Bob will do the reverse process, and Bob will get back the message. Now we'll talk about what Oscar can do. That is the all about the cryptanalysis. So suppose Alice and Bob, they have used the encryption function as DES, the block cipher, to encrypt their message, which is a 64-bit message, for their communication. Okay. Now we want to know what Oscar can do here. Any questions so far? Okay, so we have this. Now this is basically a non-plain text attack. We have seen in the earlier class we have 4 basic attack models. One is the what are the models we have seen? One is first one was ciphertext only attack. So there we have only Oscar is only having the ciphertext, because Oscar has full control on the Oscar can see the public channel. So ciphertext obviously Oscar should have. So that is the ciphertext only attack. No other information we are giving. So Oscar only have the ciphertext, that is good. And then we have seen the non-plain text attack. So here Oscar is having some plain text and the corresponding ciphertext. Maybe some old messages and the corresponding ciphertext. So that is Oscar is having, and the challenge of the Oscar is to get the key and the current plain text by seeing the current ciphertext. And then Oscar can choose the plain text, chosen plain text attack. That means Oscar can choose the plain text and can get the. So that means we are giving the temporary access to this encryption machinery to Oscar, to the attacker, so that attacker can choose their his or her own plain text and can get the corresponding ciphertext. So this attack model is useful for for the attack like differential cryptanalysis, linear cryptanalysis. So there we need to have some particular type of plain text and the corresponding ciphertext. So for that we need to have that. And then finally we have seen last one is ciphertext attack. So here we have giving the temporary access to this decryption machinery to the attacker, and then we have asked the attacker to get the, and we stop that access, otherwise attacker can give the current ciphertext and get the current plaintext, and then and another goal of the attacker is to get the key. Anyway, so this four thing we have discussed in the earlier class. So now we this attack on DS, for that we will have this non-plain text attack basically. So we have a given a, so Oscar is having a plain text and the corresponding ciphertext. So this is known, one plain text. So this is known to Oscar, known to the attack. Okay. So Oscar is having one plain text and ciphertext here. So with that, how Oscar can mount the attack? So, but Oscar is not having the key. So that is, so Oscar is not having the key. So Oscar is having, so they have used DES, so Alice and Bob. So they encrypt the message is 64-bit. They encrypt the message, basically it is a DES, using the key and get the ciphertext. Okay. Now Oscar is having this message ciphertext. This is non-plain text attack. Some plain text and the corresponding ciphertext. Good. Now how Oscar can mount an attack? So Oscar is not having the key, but key is how many bits? Key is how many bits?
56.
Yeah, so 56 bits. So we have 56. What is the key space then? What is the key space?
2 power 56.
Yeah, so set of all possible. So keys are nothing but all 56. So 0 0 0 0 all zeros 56. This could be one key 0 0 1. This could be another key 0 0 1 0. These are all 56 bit. So basically, if we consider the key space, this is our key space. The size of the key space is 2 to the power 56. Because all possible. So these are all possible combination of 0 1s in the every position. So there are 256 positions. So each position can be filled by 2 ways. So 2 into 2 into 2 into 2 into 56 times. So this is nothing but 2 to the power 50. So that is the key space. So our keys are coming from here. So some keys are say alpha 1. We can use K1, K2, but K1 we have used the round keys. But if you allow me to do so, I can use, sorry, instead of K1, we can use just superscript K1, K2, K3, K4, dot, Ki, sorry, not I over here. Like this, K2 to the power 56. This many. So this coordinate of this set is this. Now Oscar has to search in this. Oscar has to search the key in this set. So that is how Oscar will do. So Oscar is having the plain text and the ciphertext. So Oscar first choose a key. Say Oscar is choosing Q1. So now Oscar will give the input. Oscar has to encrypt the message in with say K1, and Oscar will get a ciphertext C1, and Oscar will check whether this is matching with the C or not. If it is matching with C, then this is our key. Is this okay? So some kind of exhaustive search. So if this is not matching, Then Oscar has to choose another key, say K2. Then Oscar will get some ciphertext. So this is DS encryption, because this was the DS encryption and decryption period. So Oscar will get a C2, another ciphertext, and then Oscar will check whether this is matching with the ciphertext given to Oscar. If matching, then okay, then we got the key. Key is nothing but K2. Otherwise, we have to choose another K3. So this is basically a for loop. For I is equal to 1 to 2 to the power 56. So this is a for loop. We just do the CI. CI is the DS encryption on this M and using these KIs. So these KIs we are choosing just randomly from here. I mean, may not be some way we choose a key and we check this. If this CI is equal to C, then we got the key. Then return the kind of thing. I mean, if you are familiar with this pseudocode, then return KI. Okay, kind of a for loop. I mean, a loop where we are doing this business. So this is the pseudocode for this attack. This is called exhaustive search attack. Exhaustive search or brute force attack, because we are exhaustively searching the key in a key space. And so what is the time complexity? For how much time we are spending for this attack? Any idea? We got this attack, we are just choosing a key and we are just checking whether it is the right key or not. So for that we need to do the encryption. We have the aim, so we encrypt it and we got some ciphertext. So for this KIs, we choose a KI and we have the message aim. We get some CI. We check whether this CI is matching with our C or not. If it is matched, then Eureka, we got the key. The key is our KI. So this can run how many times in the worst case? What is the time complexity for this kind of
2
attack?
की power n, sir.
Yeah, n is 56. So it is basically we have to run this for 2 to the power 56 times. And each time what we are doing? We are doing a DS encryption. So if we assume that for our computer where we are doing this, so is DS encryption is taking 1 second, so this will take the 2 to the power 56 second to do this attack in the worst case. Okay, so what is this 2 to the power 56 second? Any idea? We have to convert into days. How many days? Any guess? How many days is 2 to the power 56? 1 day is how many second? 1 day? 1 day is how many hours? 24 into 60 minutes into 60. This many seconds. So if we just try to convert this into 2 power, so this is roughly what? 2 to the power how much? 2 to the power 4 is 16. 2 to the power 5 we can say. 2 to the power 5 into this one is 2 to the power how much? 2 to the power 8 or 7?
6.
2 to the power 6. This one is 2 to the power 6. So how much is total? 2 to the power? Come on. 2 to the power 17.
70.
Yeah, we can take 2 to the power 18 also, no issue. So this is 2 to the power 18, 1 day. So 1 year, 1 year is how much? 365 into 2 to the power 20, 18. Anyway, doesn't make any difference much. 2 to the power 18 seconds. So again, we have to write this in terms of 2 to the power. What is this? 2 to the power? 2 to the power 20, we can say. And how much? 2 to the, sorry, not 2 to the power 20, 2 to the power 8, maybe. You can just check. Anyway, are you sleeping? Or am I lost? Can you hear me?
Yes, sir.
Yes, sir.
Yeah, so
Yes, sir.
so you just tell me, I mean, you are good in maths. So 2 to the power
26.
26. Still it not near to 2 to the power 50. So how many years we need to search this? 100 years,
More than 2
1000
years.
years, 2 is very less. 2 years means it is 2 to the power 27. 100 years, 1000 years. So it is quite,
It's in crores, sir.
yeah, so it is not possible. We cannot do in our single lifetime. So we can live maximum 100 years. Anyway, nowadays average age is little more due to the medical science. Okay, so we are just, so in that case, are we safe? I mean, we just, we, we cannot spend that many years to solve the DS. So anything we can do on this. So this is our piece. So we need to the power 56 seconds to solve this, which is few years. So this is, so any idea how to tackle this problem? I mean, so we cannot afford this many years. So what Oscar is doing, Oscar is searching over the here, right? And Oscar is just doing this encryption. Oscar is just doing this DS encryption. Okay, I'm checking this. So now, and if it is not happening, then Oscar is waiting for this encryption to complete to check with the second candidate. Now suppose Oscar, that means what? That means Oscar is having a single computer to do that. But suppose Oscar borrow one computer from his friend Rob, and then they to decide to do this work, do this work. So Rob is also having another computer. So both are adversary, both are attacker, or both are good friend. Okay. So then if we Rob is also on having another computer, another processor, then what we can do? We can divide the key space into half, half. Then we can, Oscar can search here, and Rob can search here. So Rob will take a key from this space, this partition, and then Rob will just do the same thing, because Rob is having now one processor to do that on computer to do that. So now this way, how much time we can, what is the time complexity? So they are doing this business in parallel simultaneously. I mean, it's not waiting. Rob doesn't matter where Oscar is, and Oscar is also not waiting for the Rob result. But once somebody got the key, then they'll say, okay, Eureka, I got the key, so no need to search further. So now tell me, if this is the scenario, if there are two processor or two computer is running in parallel to do this business, to do this search, exhaustive search, then how much time we are saving? What is the time for this? time complexity?
2 power 55.
Yeah, it will just reduce by half because we have two computers. So it's 2 to the power 55 seconds. That is not a much gain because it is again some.
Sir,
Yes.
we are doing a linear search. What if we our change our searching algorithm?
Now, if you do any search, if you do, we are not doing linear search. We are taking the key in some way, the key from the. So, if you do any search in the worst case, we are talking about worst case time complexity. That means, if you in that algorithm, if you are familiar with, we have three type of analysis we do, like worst case, best case, average case. So if you are lucky, then you will get, or if Oscar is lucky, Oscar will choose a key and will get the, and that will match with CI. That will match, that CI will match with this. But we cannot assume that. We have to talk, when we talk about time complexity, usually we consider the worst case time complexity. So for that, we need to see, in a way, Oscar is keep on searching, and at the end, after, so it's not kind of linear search. You can do the linear search, there is no problem. So
Sir,
this is
but we are
our,
one by one, right? Like
we are doing
we
one
will.
by one because we have only one computer. Oscar is having only one computer. So Oscar has to wait. Oscar choose a key. If you like linear search, okay, fine, no problem. This is our K1 say. So Oscar will have one computer. So Oscar will give the input to that computer, do the this thing like encryption, and then get the CIs and check whether this is. Then after this check, Oscar can choose another key like this. So this is a sequential executions. This is a question.
I was telling sir, if we do other search, binary search or something else, can we reduce the complexity?
No, I mean how to do, you just to need to, you just need to pick a key. That's it. So whether you are doing sequential way or you are doing random way, it doesn't matter, because in the worst case, you have to exhaust this back. Because in the
Yes.
worst case, you okay.
Oh,
Just
okay, sir.
okay. So that means if we have some more processors, then we can do something better. But two processor is very less. So suppose, but if we have many processors, if we have instead of two, if we have say 30 processor, 2 to the power 30 processor, 2 to the power 30 computers available. Basically, what we need, we need to do one PS encryption. So for that, we can just design a chip. So for that, we'll take the two input. One is the plain text, which is known, and another one is the key which we are choosing. And then we can just do this business. So suppose we have this many processors, then what we can do? We can just break it into, we can just partition this space into this many disjoint sets. The how many computers we have, how many processors we have, and then we can. So they are running in parallel. So we can assign one processor to this to search, one processor to this, one processor to this, like this. So this is what is called parallel computing, like this. And they are disjoint. So they have just running in parallel. They are just doing the searching in the particular assigned back. So we have a bigger back. In that back, we have just good. So in that case, what is our gain? So they are running in parallel, and then so basically, this we can design a chip where these are the processors running in parallel, and there should be have to have some connections over there so that they can contact with each other. So this is processor 1, processor 2 kind of thing. Processor 3, processor 4, processor 5, processor 6, like this. So now What is the time complexity? The total time is 2 to the power 56 seconds for a single processor, but if we have 2 to the power 30 processor, it will reduce to how much? 2 to the power 26 seconds. This could be less than 3 days. You can check it out. Or if we need more, then we can increase the processor. So this is the work done by Electronics Founder Foundation, EFF. This is the US company, electronics company. So they build they build a hardware, they build a chip, hardware chip where they have embedded many processors, and they have designed this so that they can have this DS encryption, and they have this connection. So that is by the Electronics Founder Foundation. So that is near about which year? 1996, something like that. Okay, so DS is broke. So DS is obviously we need to have some money for this, because if we increase the processor speed, if we put the more processor, then the money, we need more money, and then the time will be so reduced. So that is obvious, because if you are making a payasam, you need ज़्यादा गुड़ डालोगे तो ज़्यादा मीठा होगा ना. So but uska cost bhi hai, so you have to think of that trade-off also. But they spend something like 2 to 3 lakhs US dollar that time. Yeah, so that is the attack. That is called exhaustive search attack on DES. So this is a generic attack. Generic attack. Generic means, see here, to do this attack, we did not go inside the design of DES. So what matters? The key size only matters. So we know DES is a block cipher which is having key size 56 bit. So this attack can be mounted to any other block cipher which is having same key size. Doesn't matter, because we are not really looked into the inner design of the DS. So that type of attack is called generic attack, because we can do the same attack on the other place with the same situation. So only thing we need to have, our processors should be able to encrypt that block cipher. So that sense it is generic. So there are some other type of attack which are called non-generic attack. So there we will really look at the design part of the cipher, of the block cipher, and we'll see whether we can get some loophole there, like whether we can get some linear relationship between the plain text, key, ciphertext, or we can have some differential characteristics. We'll see that when we talk about this. So those are basically non-generic attack. So some examples are differential cryptanalysis, linear cryptanalysis. So they are non-generic attacks. So those attacks are design specific attack. Like we have to look at the design to get some drawback over there. So this is the so DS is not only broke by this exhaustive search attack or generic attack, it is broke under this non-generic attack also. So full round DS is broke by differential attack, linear attack. So there are other type of attack on DS. So DS is completely broke. Any question? Are you there? Very difficult, because
Yes, sir. No question, sir.
yeah, so online class is very difficult. I mean, I cannot see you, you cannot see me. I could open the video, but I thought it will hamper our this connectivity. Like my experience is, if we off the video, we get the better signal. But sometimes if you want to see I am sleeping or not, then we can do that. Okay, so yeah, so bad news. DS is broke. But it was standard. It was standard by NIST. And it was very much useful for encryption, bulk encryption. I mean, okay, so what do you mean? Suppose Alice has a message which is more than 64 bit. Then how Alice will use this block cipher? So we have two parties, Alice and Bob. Okay, so they have agreed with this. About the DS they are using. So this is 56 bit, 56 bit. Now they are using DS. They have the DS and they are very fond of DS. So yeah, but the problem is if they have a message M whose size is 64, then there is no issue. They can just put this message M, and with the key they can get the ciphertext. And this ciphertext Alice will send to Bob over the public channel, and Bob will receive it, and Bob will decrypt it. DS decryption. Yeah, so Bob will use the DS decryption using the same key and can get back the message back. Now the question is, if it's not, it may not have the say exact size of the block cipher. Not only DS, this is for any block cipher. Suppose Alice has a message which is more than 64 bits, say 1. So bulk encryption means, suppose we are conducting a GATE exam, and IIT Kharagpur is the coordinating for that. I mean, so IIT Kharagpur is having the control on the exam paper. So now at the time of the exam, IIT Kharagpur wants to send that exam paper to other IITs, say IIT Bombay. So how to send? So the exam paper is a big size. So then it has to do some sort of encryption. So that thing. So anyway, so my question is, if we have more than 64 bits, then what to do? Any idea? How to encrypt that? So if the Alice has more than 64 bit message, so but Alice has a encryption function which is 64 bits. So what Alice will do? Alice will break this message into 64 bit blocks. Dot dot dot. Last block may not be 64, so you can add some dummy things in order to apply that black DS. So you use DS encryption. This is x1, x2, x2020. 2020 is not a good year, so you can write 2021 with the hope that Corona will go. DS y1, y2. So the same key, they have the same key, I mean the key. So you use the key over here, y3 and so on. DS encryption y2020. Okay, so now Alice will send this bigger message y1, y2, y2020 to Bob. So what Bob will do? Bob will receive these y blocks, y1, y2, like this. So Bob will decrypt it. Bob will use the decryption algorithm, DS decryption algorithm, with the same key, and Bob will get back the x1, x2, and so on. This is the very obvious way we can think of doing the encryption on the message which is more than 64 bit. This can apply for any block cipher of that size. If it is L bit, then we'll break it into L bit blocks. Then is this clear? Because we cannot guarantee that our message will be always 60. If it is 64, okay, fine, good. We can just apply the one-time DES. Otherwise, if it is more, then we just break it. That's why it is called block cipher. We have a block. We have a fixed length block. In that block, we encrypt and we send it to block. Okay, so this part is okay. We'll talk about more on this part because this comes under modes of operations. Modes of operations. So this has a drawback. This kind of straightforward modes of doing this business is having a drawback. We'll see that. We'll see in details of that. There are many others, so we can do this business. But this is the thing. So we can just let us come back to DS. So DS is broke. Now, once DS is broke, then we have to think for some new standard. We have to think for a block cipher because block cipher is very much useful for bulk and for more. I mean, if your message is big, we can just use the block cipher because it is very fast. I mean, so far we don't have anything to compare, but we'll see it is very faster than the other like public key crypto system, all these things. So we prefer to use block cipher for encrypting a message whose size is more, the bulk encryption. So anyway, but so we need to have a standard, new standard. So what we do first, so we have a ready-made thing. So that is our human nature to not to give up. No, I mean if you have a, you already have a DES. So people are thinking, okay, instead of design a very new block cipher on a scratch, we can just think for something with this DES to make it secure. So that was the first attempt. That was called triple DES block cipher. That is the first attempt they made. And so what is triple DES? So what is the problem of DES? Why it is broke? Any quick answer? Apart from that differential and linear cryptanalysis. But what was the drawback? I mean, major drawback of DES. There are other drawbacks also because DES is box. There are many complaints on that, how these data are coming, it is not. But those are okay. I mean, if it is a good cipher, we can just ignore those things. A good boy can do many bad things. No, not like that. But anyway, so tell me, what is the problem
So
with
the
this?
key space is reduced by increasing the number of processors.
Yeah, so problem is with the key size. So DES is problem with the key size. Key size was very less. Key size is 56 bit. Now, if it is more than 56 bit, say if it is, say, for example, if we have a block cipher whose key size is 128 bit, for example, for AES key size is 128 bit. Then we are safe in the sense of exhaustive search. And then if we have many processors, even if we have say 48 processors also, then it will reduce to 2 to the power 48. That is also how much? 2 to the power 82nd, even 68. So see, if the processor, if we take more, then we have more expense. No, I mean that is also a trade-off between this. So the key size. So key size is the major role play into this type of attack. So the people started thinking, okay, why not we increase the key size? We'll use the same design of DES because it's already there. Instead of making a new block cipher from crash, we can use the same DES, but only thing we want to make the key size more than say 100 bit, so that to avoid this type of attack, exhaustive search. Good. So what to do? So they decided to make this key size double. So double means how much? 112. So they want to have a block cipher whose key size is double. So double means 112. Block size is same because they are basically going to use the DS. Only thing they are want to key size double. So let us know that block cipher, that is called triple DS. Triple means we are going to apply the DS 3 times. That's why it is called triple DS. So yeah, so we have a key. Key is 12112. So that key we break it into two parts. First 56 bit, second 56 bit. Why we are doing that? Because we want to use the DS. Okay, so what is the encryption for triple DS? The encryption function is basically we are applying. So we just have a DS and DS 3 times we will apply DS encryption with the key K1. This is our plain text, and then followed by DS decryption. These are DS encryption, DS decryption. Because we already have the function, we can just use this again DS. So here we use K2 because if we use the K1 again, it will give us the same message. Then the output, these are all 64 bits, so there is no problem with that. Again K1, and this is our ciphertext, and this K1. So this is our, and this K1 is the input. So this is our triple DS block cipher. Triple DS block cipher. Encryption. This is encryption. Okay. So it is a block cipher. It takes how many? So it is a block cipher which is taking 64 bit. So here I am writing the. So it is a block cipher which is taking 64 bit plain text. And what is the key size? Key size is 112 bit, and it is giving us the 64 bit ciphertext. Now, can anyone tell me how many rounds are there inside this? Is this clear, the triple DS, the encryption function? My question is how many rounds?
48.
48 rounds, because each of these guys are having, each of these is having 16 rounds. So inside that we have 16 crystal structure. Inside this we have 16 crystal structure. Inside this we have 16 crystal structure. So we have total 48 rounds, which is also huge, which may take more time to do this. But anyway, we have to use the, we have to increase the key size. So that was the first option people thought of. Okay, so this is the encryption. Now what about the decryption? What, this is what Alice will do. Now what Bob will do? Bob has to, from a mass C, Bob has to get back in. So Bob has to reverse this process. So what is the, what Bob will do? Decryption. So Bob is having C. So we first, what to do? Just look at the picture over here. Bob is here, so Bob has to get back message. So Bob will do the just the reverse thing. See, this is encryption. Bob will do the decryption of DS using the same key. Then followed by, since this is a decryption, Bob will do the encryption of this using the same this key K2, and then so on and so forth. So this is the thing. So Bob will do the first using K1. This is C. This is Bob will do the decryption, and then followed by using K2 encryption, and then followed by K1 begin decryption, and Bob will get back the message. So this is triple days decryption. Okay, so yeah, so is this secure? Well, this is secure in terms of the exhaustive search. Exhaustive search is not possible, even if we have many processors with guides, because it is the key size is 112. So it will take 2 to the power 112 seconds. Even though if we have some say 2 to the power 52 processors, then also it will reduce to 2 to the power 60 seconds. That is also huge. Okay, so that sense it is not. I mean, it's very difficult to make a hardware, or we can do it in software like that. So okay, so is the safe? We can make this as a standard. NIST can announce, okay, now we got a new block cipher, although not new, but at least we can just. So is this okay? I mean, is this secure? What do you think? Is the triple dash secure? Will you use it? भाई कुछ बोलो, yes or no? No. Why? Why it is not a popular one? See, apart from this generic attack, we have other attack also, non-generic attack. Those are basically linear attack. Then we have differential attack. So those are there in our DES, and this triple DES is using the same functionality, same algorithm. We are basically using DES 3 times. So we are using same function. So that means in there also we can mount this type of attack, because these are the drawback in the design. So that we are using same design. So this type of attack will exist there also. And also this is the round is 48 rounds, which is not very much acceptable to that. But anyway, we do have this attack. So that's why they decided not to make it standard. So then they give up, and they just give up means give up with the DES. So they give up they decided to buy a new TV. Okay, old TVs, although the sentiment is there, but anyway, so then what they do, NIST announce a open competition. That was, anyway, I have to check the years. Maybe it was 1997 or something like that. Please check these years. It is there in the lecture notes. They open a competitions. They just announce, instead of design by themselves, they announce a competition to submit the block cipher, so that they can they can choose one. So now that time many people, many cryptographers who are working, they just jump into the design the block cipher. So they struggle hard to design the block cipher in the first workshop, or in the first round. There are many submissions were there. Say more than 100. So among them, they choose 60 block cipher in the first round, because other block cipher, there are some fault, and it was open competition. There is a public website. Everybody can see others' block cipher, and they can attack, and they can have a paper, and they can finally get the PhD degree. So there is a huge competition going on. But in the second round, among this, they reduced to 6 in the second round. And name of the block cipher of these are like, I don't remember all the names. RC6, Two-Fish, these are the name. Rindel, and then Serpent. Anyway, these are other 6 block ciphers was there in the second round, I mean pre-final round, and finally they choose among these, they choose one, because that has to be one has to give the prize. There is no tie kind of thing. So tie could be there, but one has to give the gold medal in the Olympic. So that guy is this block cipher, Rindel. So Rindel is the name of the block cipher that is designed by 2 cryptographers, Belgium cryptographer Vincent Richman and John Damian. So that time they are doing in postdoc in MIT. So based on their name, the Rindel name came. So this is a block cipher, and this is still today, and they gave the stamp. Still today, this is the standard, and this is the standard by NIST. Still today, there is no attack on full round Rindel, and this is our AES, Advanced Encryption Standard. So it's still today it is secure. So if you use the full round, this is 10 round. If you use the full round AES, then you are safe. There is no harm in that. Okay. Anyway, we'll do the Rindel this block cipher because it involves some maths part, like little bit of finite field. Don't worry about that. We'll discuss those. Not much, very little. Okay, so I think next class we'll start stream cipher. So before that, let us take an assignment, coding assignment. So maybe this is 2 assignment I will give. One is the implement all classical cipher we have discussed in the class ciphers. That means substitution cipher, scissor cipher, permutation cipher, Clayfair cipher, and then implement. Implement means in C language. You need to show me the code. Implement DES decryption. Anyway, both you can do DES, both the encryption and decryption. So for decryption you need to work little hard about that. But anyway, we are not inverting the small f. So these 2 assignment you can submit next week. And next week also we are planning to have a quiz on Thursday, and the syllabus will be up to today's lecture. So the DES up to DES. So I'll send you a mail of the details of that. So yeah. So any question before we stop?
Yes. Sir, we can only use C language, or we can use any.
No, you can use C language. Other language, if you use Java, Python, all these things, then you can get the ready-made functionality for there. I don't want that. I want you to learn this thing. I'm not asking you to use the assembly language, just C language. C is the mother of all language, and moreover, I know C only. So anyway, so you try to, because you are learning C, right? All the CSD student, you are having C programming now. Take your time to do it. Okay. Let me stop the recording.
Sir, next week when exactly?
End of next week, you have exam on. You have exam